The first error bound we're going to look at is the easier one, the alternating series error bound. And really important to note, this is only going to help us for alternating series, which means series whose terms switch off signs, positive, negative, positive, negative. So here is the alternating series error bound. The difference between the infinite sum and a partial sum, which is just a fancy way of saying the error, has to be less than the next term. At any point in a converging alternating series, once you've added a certain number of terms, you're going to be off by a little bit from the final sum, but you can't be wrong by more than the next term. And we'll see how this works, and we'll see it's really easy to use this. So here's an example of a power series. For this power series, I want to estimate f of 1. Now keep in mind, this is not one of our known series. I'm not like trying to find e to the first or ln of 1 or anything like that. Like, this is just some random power series. But I want to know, what is f of 1 of this power series? Well, if we use the first 3 terms of this series, well, first of all, actually, let me plug in 1. If I plug in a 1 here, that numerator becomes 1 minus 2, or negative 1 to the nth. And that's how we know that this series is alternating. And if we try to use the first 3 terms to approximate that, we can add the first term is positive negative 1 to the 0 over 3 to the 0 times 0 plus 1. And the next one will be negative, because it's negative 1 to the first, over 3 to the first times 1 plus 1. That's 3 times 2. Next term will be positive, because it's negative 1 squared, over 3 to the second times 2 plus 1, so that's 9 times 3. And if we do the math here, we can make a common denominator of 54. So that's 54 over 54 minus 9 over 54 plus 2 over 54. And that is 47 over 50. That is my partial sum after 3 terms. The question is, how close is that to the infinite sum? That's what the error bound is for. So the error bound, again, looking back to this definition up here, the error has to be less than the next term. So that means that our error, which I can use this notation from above, or if I want to, I can call that the remainder. I should put a 3 in here because we have done 3 terms. Or I could call it the remainder after 3 terms, has to be less than the next term. Well, the next term would be the 4th term. Which, by the way, be careful. The 4th term is when n is 3, because we started counting when n is 0. Like, this number isn't always the same as the number that gets plugged in here. So be careful about that. Okay, so the 4th term after 1 over 27 would be, it's negative, but we're putting in an absolute value, remember. So I don't really care about that negative in the numerator. Over 3 to the 3rd, that's 27, times 3 plus 1 is 4. 27 times 4 is 108. So my error bound is 1 over 108. So 47 over 54 was my partial sum, and the amount that I could be wrong by is 1 over 108. So what we're going to do is put those two numbers together to give a range of values where f of 1 must fall. So the center here is 47 over 54. That is my best guess. But I could be wrong by as much as 1 over 108 in either direction. So both of these distances are 1 over 108, which means that the lower value The lowest possible number that f of 1 could be is 47 over 54, which it's convenient we have common denominators, pretty easy here. 94 over 108 minus 1 over 108 is 93 over 108. And the highest is 94 plus 1 over 108. So that means f of 1 is somewhere between 93 over 108 and 95 over 108, which is a pretty narrow scope if we take a look at, just get those decimals from there. Dividing by 108 isn't that different from dividing by 100. We're somewhere between 0.86 repeating 1 and 0.87962 repeating. So that's a pretty narrow scope between 0.86 and 0.88. But what if we wanted that to be even more narrow? Say, for example, we want it to be correct to 4 decimal places. Now, this is a weird little thing here that happens. We're not going to get too deep into why it happens this way, but just know that if you need to be correct to at least 4 decimal places, that means we need our error to be less than 0.0005. It's 4 zeros and then a 5. We're not going to get into why that's the case on this video. But what that means is that the next term, well, I should say the absolute value of the next term, has to be less than 0.00005. And we know that the next term is, again, I'm going to ignore the negative because it's an absolute value, 3 to the n plus 1 over n plus 1 plus 1. So all I need to do is figure out what term we need, or what n needs to be, in order for this to be less than 0.00005. And there's no reason to solve this algebraically. We can't, actually. Like we don't have methods for solving that algebraically because there's both exponential and linear. We can't solve them both at the same time. But that's okay. We don't need to. What we can do instead is just graph this here. And again, it was 1 over 3 to the, got to put this in parentheses, x plus 1. I'm just going to switch to x so it's easier to look at it on Desmos, times x plus 2. And what I want to know is when is this less than 0.00005? Now, obviously, I don't need my y-axis to go all the way up to 5. So I'm going to zoom in here using that shift button to zoom in just one direction at a time. And I want to know when it's less than 0.00005. That's 4 zeros and a 5. So like right in there. So it's right there. If I want to know exactly what that is, I will just graph the line y equals 0.00005 and look for this intersection. It happens right here when n is 6.109. Now, obviously, n can't be 6.109 because n has to be an integer. You can't have 0.1 of a term. What this tells me is that when n is 6, the error is a tiny bit too big. By the time the n is 7, the error is under our requirement. It is 0.0000169, which is less than what it needs to be. And so that means that as long as n is bigger than 6, our error is not too small. So n must be at least 7 terms. So we need 7 terms in order to make sure that we are within 0.00005. You can kind of get a sense of how this is a useful idea. When we talk about computers calculating things that are not exactly calculatable, like the sum of infinite series, it's important to be able to say, all right, well, if I need a certain level of precision, how much work do I need to do? So a calculator can be programmed to add up 7 terms of this power series and use it to find f of 1. The truth is that this is something like what your calculator does every time you ask it to find like sine of 1. It has been programmed to know what the power series is for sine, and it basically plugs the number 1 into your power series, and it can't do it infinitely. Calculators can't add up an infinite number of terms, but somebody has figured out, using a method very similar to this, how many terms it needs to add in order to make sure that the precision is precise enough for the purposes of whatever you're trying to do with it. That's why if you look at a very, very, very advanced computer, it might give you a slightly different answer for the sine of 1 than a regular one, because it might have been programmed to be more precise for more decimal places. We'll look at another example here that's similar, kind of give you the same idea. So the example we're going to look at is the Maclaurin series for the cosine of x. We're going to use the Maclaurin series to estimate cosine of 2. So first, let's just remind ourselves what cosine of x looks like. It is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, which I actually shouldn't have written because we're only looking at the third partial sum, which means the sum of the first 3 terms. So the cosine of 2 would be approximately, approximately 1 minus 2 squared over 2 plus 2 to the 4th over 4 factorial, that's 16 over 24. So that's negative 1 plus 2/3 or negative 1/3. That is our estimate for the cosine of 2. Negative 0.33 repeat. But we understand that since we stopped after 3 terms, that's not going to be exactly right. It's going to be off by a little bit. So the question is, how much could that be off by? The maximum value of the difference between our polynomial and the cosine of 2, the actual value. So the actual, well, another word for that is the remainder. The remainder after 3 terms has to be less than the 4th term because this is an alternating series. That's right, less than the absolute value of the 4th term. The absolute value of the 4th term would be 2 to the 6th over 6 factorial, or 64 over 720. Now it happens to be negative, but we only care about the absolute value of it anyway. Which means that our answer is somewhere between negative 1/3 minus 64 over 720, which we can reduce that quite a bit. Divide them both by 8. That's 8 over 90, which is 4 over 45. So the lowest that the cosine of 2 actually could be is negative 1/3 minus 4 over 45. And the biggest it could be is negative 1/3 plus 4 over 45. So our maximum error is 4 out of 45. If we take a look at what these decimals are, negative 1/3 minus 4 out of 45, and negative 1/3 plus 4 out of 45. So, I forgot my forehead. So the actual cosine of 2 is somewhere between negative 0.422 and negative, what was it, 0.244. That's fine. Now, because we know that the 4th term is negative, that means the 4th term brings us down this way. And the next terms are much smaller. So we're actually going to be a lot closer to negative 0.422 repeating than 0.244 repeating. But technically, that's not something we know just by looking at the error bound. And if we do want to compare that to the actual value of the cosine of 2, we can see it is actually quite close to our lower bound. Now, we only did 3 terms. So our error bound was actually, not that small, 0.08. We're only correct to 1 decimal place, not even. But had we done more terms, you can see that we would have been a little bit closer. Hopefully that gives you some sense of what the idea of an error bound is for. And in the next video, we'll take a look at another kind, what we can do when the series is not alternating.